Okay, good morning to all of you. We are nearing the completion of design of compression members. So the final part of this is how to design any column which does not satisfy some of the conditions that we saw. Okay. One of the things that we have to see is we need to see what a slender column is. Okay, so basically we'll be dealing, I'll not be doing a problem, I'll just be telling you the concepts behind slender columns. And I'll send you something, you can do a self-study and do probably one problem will ask you to do as an assignment. Okay, so I'll just go over what this is about. So, sorry. Yeah, so till now you have been dealing with this condition that the compression members that you have designed so far, you have ensured the condition that you've ensured the condition basically that they are going to be, short columns in the sense that their effective length by the shortest dimension should be less than 12. Okay, so this is the condition on which you have designed most of the columns which you have designed till now. Now, it's not always the case. Sometimes this condition may be violated. Okay, for general buildings, we would usually be satisfying this condition. Okay, we will always ensure that we have a short column in a normal construction, normal buildings and all. But in many cases, we may giving a short column may be a bit. You may end up with really bulky columns, very wide, very thick columns. You may end up with, especially if you have a very large height to support. Okay, so in such cases, sometimes you may have to resort to violating this particular condition that it is less than 12. So what happens then? Okay. So any column which is beyond that limit of 12, we call that as a slender column. Okay. So here there are some conditions with respect to slender columns. First thing is you need to know what the effective length is because when you come to more than short columns, for slender columns this effective length this effective length becomes really important for slender columns as compared to short columns. I think you would have heard of effective length already once, I suppose. Have you heard of this word anywhere else in mechanics of solids? Have you heard of this word, effective length? Have you come across effective length in mechanics of solids? It's a simple yes or no question. Have you come across or not come across? Is it a yes or a no?
No, sir.
Or not? Sorry, not come across effective length. Okay. You come across that Euler buckling theory, no? Pi square A by L square. Have you have come across that, right? Pi square A by L square.
Oh yes, sir. That depends on the support, like supporting condition.
Okay. So what depends on the support there in that formula?
There will be L effect.
Which one? It is like that. Okay, yeah. So how do you actually decide the length based on the support conditions? Do you have any parameter there? So basically that formula itself, no, it is it's not simply pi square A by L square. It is slightly different, not different. It's slightly one more term is there. Sorry, it's basically. See, basically it is PCR equals pi square A by pi square A by. It is KL whole square actually, where K is known as effective length factor, and this effective length factor depends on your boundary, your end conditions, okay, or your supports. And for a simply supported column with a hinge and a vertical roller on top, or vice versa, this becomes 1.0 if it's such a column. So that's why in the problems which I have done till now, so I told you that I'll come to effective length factor later, and for this problems let us assume that the effective length factor is 1, meaning that I had considered all the columns that I designed till now as simply support, okay, or a column like this basically, one end hinge and other end having a roller with a load like this. So when this is the case, you have 1.0. So like this, there are several conditions given to you in Annex E. I will come to that soon. So sticking with cylinder columns, we have this condition that whatever be the case, the length between the restraints should not exceed 60 times the lateral dimension. Meaning that my in words it says that my it's unsupported length, it's not effective length. It's unsupported length. You can read that. Okay. So the unsupported length. So therefore, I'll say L0 should not exceed, okay, 60 times the least lateral dimension. Okay. So that's what this is specified over here. Okay. So sometimes you may have restraints in a column. So for example, restraint means, say for example, this column is really long and somebody wants to arrest this column. So they may give a restraint here. Okay, such that its effective length is cut short by. It may not be exactly cut short by 2. It may be something calculated based on that. Okay, but anyway, that's something much more than what you need to know. So anyway, these things we've seen, minimum eccentricity and all those things. Okay, so this is as far as the definition of slender column is concerned. Then when you come to design of compression members, you have some idea on how to design a slender column. Okay, so these things we saw yesterday. Members subject to combined axial and uniaxial bending. So here it's written why we use the SP16. Okay, design of member subject to combined axial and uniaxial bending involves lengthy calculations by trial and error. In order to overcome these difficulties, interaction diagrams may be used. Okay, so this is why I said that if you have a bending plus compression problem, go ahead and use SP16 without needing a permission to do so. This thing also we saw yesterday. Okay, this interaction formula, the PZ values, the PZ by PZ ranges for alpha, all these things we've seen. Now coming to slender columns, we see that we have some conditions here where basically it involves what basically it says is the design of slender compression members shall be based on the forces and the moments. So this is the keyword, the forces and the moments determined from an analysis of the structure. Okay, including the effects of deflection and including the effects of deflection on the moments and forces. I'll come to what this statement actually means. Okay, this is something which will be a bit new to you. So it says when the effect of deflections are not taken into account, additional moment given by 39.7.1 shall be taken into account in the appropriate directions, meaning that even if it is a purely axially loaded compression member, even in that case, you have to calculate 2 moments given by this formula, and you have to check the column for these moments. So it becomes like a biaxial bending problem, which you have to do a check for. Okay, so these are the points which you need to remember. Okay. And it also has one extra condition given that the value is given by equation 39.7.1, which is the one we saw above. So these two. These may be multiplied with the following factor. Okay, equals if it's 1, it should be multiplied by 1. Otherwise, it should be multiplied by PUZ minus PU by PUZ minus PB. Okay, so what are these things are given over here? PU is the actual compression. PUZ is the same PUZ which you calculated yesterday for a biaxial bending problem. And PB is the axial load corresponding to the condition of maximum compressive strain of 0.005 in concrete and tensile strain of 0.002 in outermost layer of tensile. So this is something which is a bit it's not something which is very directly apparent to us how we should calculate PB. So for your sake, whenever when you're doing your problem, you may actually probably just neglect this multiplication factor and just go ahead with using these moments alone, meaning that you can just consider the factor to be 1 for your benefit, okay, for your ease, okay. So, but anyway, this is given, so I just wanted to say it. And the effectiveness factor, that is important, so that is given in Annex E. So Annex D, I hope you remember, it's your two-way slabs coefficients. The next annex is Annex E. Okay, there are a lot of things in this. These are all a bit. Those who go into stability and those things, they'll only then they'll understand what these things mean. These are basically known as in the charts. Somebody's name is there. So his this is known as some particular charts. So basically, these gives effectively factors for columns in the frame. Okay. See, for example, if you have a frame like this. And you want to know exactly what should be the effective factor to design this column for. How do you design? Okay, so these are so it's for this purposes that these effective factors are given. This against sway with a restraint against sway, without restraint against sway, and you also have the same thing for column in a frame with no sway also. So you have two things, but anyway, this is just for your extra information. It's not something you'll directly use. This is what you will directly use in your BTech, this course which you're doing. So basically, you need to look at the column and see what is the effective factor that you should use. So they're given two values, theoretical and recommended. Okay, so there's a difference between this theoretical and recommended. And so you can see 4 things over here. They're shown in words what the conditions of the supports are. They've also shown it by drawing it. Then they mentioned theoretical value of effective length and recommended value of effective length. Okay. Okay. So when you read it, you should know what it means. So it's the first one says effectively held in position and restrained against rotation. So which type of a support restrains both movement and rotation?
Fixed.
Fixed. Okay. So if you have a column which is fixed. Okay. Okay, if you have a column like this, okay, you have such a column, then for this column it says you can use a recommended effective length factor of 0.65 while the theoretical is 0.5. So what this theoretical 0.5 means is, okay, so the theoretical value when I say is what you use with the Euler formula, that is known as theoretical value. So if you have a fixed column, you will be using pi square EI by for k you would be substituting 0.5 into L square. So this becomes so in fact when you do this, you see that you will get 4 pi square EI by L square. So you see that when you're as compared to a simply supported column which is having pi square EI by 1 L square, okay, so this is almost 4 times. Okay, this is theoretically speaking, it is exactly 4 times. Okay, it's exactly 4 times the critical load which you get for a simply supported column. So when your boundary conditions become more and more rigid or more and more strict, you have a greater capacity, you have much more greater critical load, meaning that it doesn't buckle easily. Okay, it takes 4 times the load to make it buckle when you have a fixed column. So this is the theoretical value of the effective factor, but here in the code book it says the one you are recommended to use is 0.65. Oh, sir. Sir. முடிஞ்சா அனுப்புறீங்க சார். அது ஐ திங்க் போட்டிருப்பாங்க நினைக்கிற பிபிடியில். எப்படியும் நீங்கள் உங்கள் மினிட்ஸ் தனியாக அனுப்பிச்சிருக்கீங்க சைன் போட்டு. ஸோ அதனால அது யூஸ் பண்ணிப்பாங்கன்னு நினைக்கிறேன். பட் வேணும்னா அனுப்பிச்சு விட்ருங்க சார். இன்கேஸ் இப்போ ஆஃபீஸில் இருந்தீங்கன்னா வேணும் அனுப்பிச்சு விட்ருங்க. ஓகே ஓகே. ஓகே ஓகே. ஓகே சார். ஓகே.